Press the power button on a modern computer, and an invisible storm begins. In a fraction of a second, electrical signals race through the processor, memory wakes, storage devices respond, graphics appear on the screen, and software begins to organize billions of instructions into something that feels effortless. To the person sitting at the desk, the process seems almost magical. Yet beneath every window, every image, every calculation, and every line of code lies one tiny idea repeated on an almost unimaginable scale: the transistor. A transistor is a microscopic electronic switch. It can control the flow of electricity, amplify a signal, or represent the basic on and off states that digital machines use to process information. Modern processors contain billions of them. Memory chips depend on them. Graphics processors, storage controllers, network adapters, and almost every other major electronic system inside a personal computer are built from descendants of the same principle. Without the transistor, the computer on a desk would not simply be slower or larger. The entire idea of affordable personal computing would be difficult to imagine. But the transistor did not begin as a computer invention. It emerged from a very different problem in an era when electronics depended on glass tubes that glowed, consumed large amounts of power, generated heat, and failed often enough to keep technicians constantly busy. To understand how a tiny solid device helped create the modern PC, we have to return to the 1940s, when the electronic world was dominated by vacuum tubes, and when 3 scientists at Bell Laboratories were trying to find a better way to control electricity. Before transistors, the vacuum tube was one of the most important components in electronics. A vacuum tube could amplify weak signals and act as an electronic switch. It was essential to radio, telephone systems, radar, and early electronic computers. Inside a typical tube, electrons moved through a vacuum between metal elements sealed inside a glass enclosure. By controlling that flow, engineers could manipulate electrical signals. The technology was powerful, but it came with serious disadvantages. Tubes were physically large compared with later semiconductor devices. They required heaters, consumed significant energy, generated substantial heat, and could burn out. In small radios, these problems were inconvenient. In large computers, they became enormous engineering challenges. One of the most famous early electronic computers, ENIAC, used roughly 17,000 vacuum tubes. It occupied a large room, consumed huge amounts of electricity, and required constant attention. Imagine trying to build a machine 100 or 1,000 times more complex using the same technology. Every additional tube meant more heat, more wiring, more power, more space, and another possible point of failure. Computer engineers had reached a paradox.
To create more powerful machines, they needed more switching elements, but the switching elements themselves were making the machines harder to build and maintain. A smaller, cooler, more reliable substitute was desperately needed. The solution would come from a class of materials whose electrical behavior seemed almost mysterious at the time: semiconductors. Bell Laboratories, commonly called Bell Labs, was one of the most important industrial research centers of the 20th century. Its parent organizations operated a vast telephone system, and that system presented difficult technical problems. Telephone signals had to travel over long distances without becoming too weak or distorted. Amplifiers were needed throughout the network, and vacuum tubes performed that job, but they required power, maintenance, and replacement. Bell Labs researchers believed that solid materials might provide a better alternative. They had already studied crystals used in radio detectors, and they knew that substances such as germanium and silicon did not behave like ordinary conductors such as copper, nor like perfect insulators such as glass. Their behavior could be changed by impurities, electric fields, temperature, and contact with other materials. This made semiconductors both frustrating and promising. If scientists could learn to control current through a semiconductor, they might create a solid-state amplifier with no fragile glass envelope and no heated filament. That possibility brought together 3 men whose names would become permanently associated with the transistor: William Shockley, John Bardeen, and Walter Brattain. Shockley was a brilliant and ambitious physicist who led a semiconductor research group. Bardeen was quiet, deeply analytical, and exceptionally strong in theoretical physics. Bardeen was an experimental physicist with an extraordinary instinct for building and measuring delicate laboratory devices. Their personalities were different, but their skills were complementary. And for a brief period, those differences became the ingredients of a technological breakthrough. Shockley had been thinking about a solid-state amplifier for years. His basic idea was that an electric field might control the flow of current through a semiconductor. In modern terms, This concept sounds familiar because field effect transistors use precisely that principle. But in the 1940s, the physics of semiconductor surfaces was poorly understood. Shockley imagined that a voltage applied near the surface of a crystal could influence the movement of charges inside it, allowing a small input signal to control a larger output signal. The analogy is simple. Imagine water moving through a channel. If a small control could regulate the flow without physically blocking the channel, that control could act like an efficient valve. Shockley hoped an electric field could become such a valve for electrons. Yet the experiments did not behave as expected. When researchers applied electric fields to semiconductor surfaces, the current inside the material often changed far less than theory predicted. Something was screening or canceling the effect. The failure was not merely a technical inconvenience. It suggested that the scientists did not yet understand what was happening at the surface of the crystal. That mystery became John Bardeen's problem. Bardeen approached the puzzle with theoretical patience. Instead of assuming that the electric field concept was wrong, he asked what invisible mechanism might prevent the field from penetrating the semiconductor. His analysis led to the idea of surface states, electrical conditions at the boundary of the crystal where charges could become trapped. Those trapped charges could effectively shield the material beneath them, reducing the influence of an external electric field. In other words, the researchers had been trying to control the inside of the crystal while the surface was interfering with their efforts. This insight changed the direction of the experiments. Rather than simply increasing voltages or repeating the same failed arrangements, Bardeen and Brattain began concentrating on the semiconductor surface itself. Brattain was ideally suited to the task. He was a careful experimentalist who could turn theoretical suggestions into physical arrangements involving metal contacts, liquids, crystals, wires, and measuring instruments. Bardeen would analyze what the measurements meant, while Brattain would adjust the apparatus and test another possibility. Their collaboration became a conversation between theory and experiment. Germanium, a semiconductor then widely studied at Bell Labs, became central to their work. They examined how electrical contacts behaved on its surface and how local changes in charge could influence current nearby. Progress came slowly. Some experiments produced amplification under special conditions, but the effect was not yet stable or practical. Still, the scientists were getting closer to a device that could control current in a solid material. During the final weeks of 1947, the pieces finally came together. The first working transistor did not look futuristic. It looked improvised. It worked with a small piece of germanium and two very closely spaced metal contacts. A thin strip of gold foil was wrapped around a small plastic wedge, and the foil was carefully cut at the tip, producing two separated contacts that could press against the germanium surface only a tiny distance apart. The arrangement was delicate. If the spacing was wrong, if the surface condition changed, or if the contacts did not press correctly, the effect could disappear. But when Bardeen and Brattain tested the device, something remarkable happened. A weak electrical signal applied through one contact influenced a stronger signal measured through the other. The device amplified. On December 16, 1947, the researchers obtained successful amplification. And a week later, on December 23rd, Bell Labs managers witnessed a formal demonstration. This was the point contact transistor. Compared with a vacuum tube, it was tiny. It did not need a glowing filament, did not require a sealed glass chamber. It promised lower power consumption, less heat, and greater durability. The object itself was modest, but the principle it demonstrated was revolutionary. A solid piece of semiconductor material could control and amplify an electrical signal. At that moment, the device was still fragile and difficult to manufacture. Nobody could simply take the laboratory prototype and place it inside a consumer computer. Personal computers did not even exist, yet a door had opened. Electronics no longer had to depend on vacuum tubes. The question of who invented the transistor is more complicated than a single name. John Bardeen and Walter Brattain produced the first successful point contact transistor, and their direct role in the decisive experiment is central to the story. William Shockley, however, led the semiconductor research group and had spent years pursuing the broader goal of a solid-state amplifier. He was not part of the successful bench experiment that produced the point contact device, and that fact reportedly frustrated him, rather than abandoning the problem. Shockley began working intensely on a different transistor design. He developed the theoretical basis for the junction transistor, in which regions of differently treated semiconductor material formed internal junctions, rather than depending on two fragile surface contacts. The junction approach proved far more suitable for reliable manufacture and became extremely important in the growth of the semiconductor industry. The three men therefore contributed in different ways. Bardeen supplied the theoretical insight that helped explain why earlier field effect experiments failed. Brattain carried out the crucial experimental work that demonstrated the first functioning transistor effect. Shockley directed the research effort and then developed the junction transistor concept that helped move the technology toward practical production. In 1956, Bardeen, Brattain, Shockley shared the Nobel Prize in Physics for their research on semiconductors and the discovery of the transistor effect. Their professional relationship, however, did not remain harmonious. The success that linked their names also created rivalry and tension, and eventually their careers moved in different directions. For the transistor to transform the world, it had to become more than a laboratory curiosity. The first point contact device was difficult to manufacture consistently. Engineers needed designs that could be produced reliably, survive real-world use, and perform well in large numbers. Junction transistors provided a major step forward, and during the 1950s, semiconductor manufacturing improved rapidly. Early devices frequently used germanium because it had useful electrical properties and could be processed with the techniques available at the time. Yet germanium had limitations, especially when temperature increased. Silicon gradually became more attractive. It was abundant. It performed well at higher temperatures. And, most importantly, it could form a stable layer of silicon dioxide on its surface. That oxide layer would later become fundamental to advanced transistor manufacturing. As fabrication improved, transistors became smaller, more dependable, and less expensive. Portable transistor radios gave the public one of the first dramatic demonstrations of what solid-state electronics could do. A radio that once depended on bulky hot vacuum tubes could now be made compact enough to carry. Batteries lasted longer, devices became more durable, electronics began to leave fixed cabinets and move into everyday life. But even this was only the beginning. Engineers were still assembling circuits from separate transistors, resistors, capacitors, and wires. As systems grew more complex, the number of connections became a new obstacle. This problem became known as the tyranny of numbers. If a computer required tens of thousands of individual electronic components, each one had to be connected correctly. More components meant more solder joints, more wires, more assembly work, and more opportunities for failure. The transistor had solved the problem of the vacuum tube, but the industry now needed a way to combine many transistors efficiently. The integrated circuit provided the answer. In the late 1950s, Jack Kilby at Texas Instruments and Robert Noyce at Fairchild Semiconductor independently developed crucial approaches to building multiple electronic components on a single piece of semiconductor material. Kilby demonstrated that circuit elements could be fabricated together, while Noyce's work, combined with the planar process developed at Fairchild, pointed toward a manufacturing method that could scale. The implications were enormous. Instead of building an electronic system by wiring together hundreds of separate transistors, engineers could create microscopic components together on one chip. Circuits became smaller, faster, more reliable, and eventually cheaper. The transistor was no longer necessarily a visible object that a technician could hold between two fingers. It could become a tiny pattern inside a larger silicon device. The number of transistors per chip began to rise. Dozens became hundreds, then thousands. Still, another major step was required before the transistor could truly dominate modern digital electronics. That step was the MOSFET, the metal oxide semiconductor field effect transistor. At Bell Labs in 1959, Mohamed Attallah and Do-An Kong developed the practical MOSFET in a striking historical circle. This device realized the basic field effect idea that had challenged Shockley and his colleagues years earlier. A MOSFET uses a voltage applied to a gate to control whether current can flow through a channel in semiconductor material. It functions as an extremely effective electronic switch. The importance of the MOSFET was not simply that it worked. Its structure could be scaled to very small dimensions and manufactured in enormous numbers on integrated circuits.
It also consumed relatively little power in digital logic, especially as complementary MOS or CMOS technology matured. These advantages made MOS transistors the foundation of modern processors, memory chips, and countless other digital systems. The first point-contact transistor of 1947 proved that solid-state amplification and switching were possible. The MOSFET made it practical to place vast numbers of transistor switches on one chip. This distinction matters because the transistor inside a modern computer is not a miniature copy of Bardeen and Brattain's original device. It is part of a technological family that evolved through decades of research. Yet without the original breakthrough, that family would not exist in the form we know today. By the end of the 1960s, integrated circuits were becoming sophisticated enough to change the architecture of computers. Early digital machines built processors from many separate circuit boards and chips. Each improvement in integration reduced size and cost while increasing reliability. Then came the microprocessor, a device that placed the central processing functions of a computer onto a single integrated circuit or a very small set of chips. In 1971, Intel introduced the 404, widely recognized as the first commercially available general-purpose microprocessor. Its development involved engineers including Federico Faggin, Ted Hoff, Stanley Mazur, and Masatoshi Shima. The 404 contained roughly 2,300 transistors. That number is worth pausing over. In December 1947, Bardeen and Brattain had demonstrated one delicate transistor built by hand on a laboratory bench. Only 24 years later, a commercial chip could contain thousands of transistors, working together as a programmable processor. The pace of change was extraordinary. More capable microprocessors followed. Intel produced the 8008 and 8080. MOS technology created the 6502. Zilog introduced the Z80. Intel's 8086 family established an architecture that would become central to the IBM PC and its descendants. Motorola's 68000 powered another influential line of computers. These processors did not create the personal computer revolution by themselves, but they made it possible to build powerful computing systems at a scale and price that earlier generations could not have imagined. During the 1970s and 1980s, computers moved from specialized institutions into offices, schools, workshops, and homes. Machines, such as the Altair 8800, showed that individuals could own programmable computers. The Apple II brought computing to a broader audience. Commodore and Atari systems introduced millions of people to software and games. The IBM PC helped establish personal computing as a standard business tool, while the Macintosh demonstrated new possibilities for graphical interfaces. Every one of these machines depended on semiconductor technology descended from the transistor. Inside the CPU, networks of transistors formed logic gates, registers, counters, control circuits, and arithmetic units. In memory, transistors helped store and retrieve data. Interface chips controlled keyboards, displays, storage devices, printers, and communication. The personal computer was a combination of many inventions, but the transistor was the element that made its internal logic compact enough, cool enough, reliable enough, and cheap enough to sit on a desk. A room full of vacuum tubes had been transformed into a handful of chips. The number of transistors that could fit on those chips kept increasing. In 1965, Gordon Moore, then at Fairchild Semiconductor, observed that the number of components on integrated circuits had been increasing rapidly and suggested that this trend could continue. The idea later became known as Moore's law. It was never a law of nature. It was an observation about technological and economic progress, but it became a powerful expectation within the semiconductor industry. Manufacturers invested enormous resources in making transistors smaller, improving fabrication equipment, refining materials, and designing more complex circuits. As transistor dimensions shrank, more could fit into the same area. More transistors allowed processors to perform more functions, memory chips to store more information, and computers to become both more powerful and more compact. The progression was dramatic. Thousands of transistors became tens of thousands, then hundreds of thousands, then millions. By the late 20th century, leading processors contained tens of millions. In the 21st century, counts rose into the billions and then tens of billions in advanced designs. A tiny silicon package came to contain more switching elements than the total number of vacuum tubes ever assembled into the earliest electronic computers by many orders of magnitude. This scaling changed more than raw speed. More transistors allowed designers to build larger caches, deeper instruction pipelines, multiple processing cores, complex branch prediction systems, integrated graphics, security engines, and specialized accelerators. Graphics processing units evolved into massively parallel devices containing enormous numbers of transistor-based computing elements. Memory technologies also advanced. Dynamic random access memory, or DRAM, uses transistor-based cells to store bits temporarily while a computer is running. Flash memory, used in solid-state drives, relies on specialized transistor structures. capable of retaining electrical charge, and therefore preserving information even when power is removed. Network controllers, USB interfaces, audio chips, Wi-Fi radios, display controllers, and power management circuits all use transistor technology. A modern PC is therefore not simply a machine that contains a transistor. It is an ecosystem of semiconductor devices containing billions upon billions of transistor structures, each performing tiny operations that combine into the behavior we experience as computing. The contrast with ENIAC is almost difficult to comprehend. A modern PC is therefore not simply a machine that contains a transistor. It is an ecosystem of semiconductor devices containing billions upon billions of transistor structures, each performing tiny operations that combine into the behavior we experience as computing. The contrast with ENIAC is almost difficult to comprehend. ENIAC required roughly 17,000 vacuum tubes to perform calculations that today would be trivial for a small microcontroller. It filled a room and consumed enormous power. A modern processor, by comparison, can contain billions of transistors in a package small enough to hold in one hand. Those transistors switch billions of times per second while using a fraction of the space that a comparable vacuum tube system would require. If engineers tried to reproduce the logical complexity of a modern processor with vacuum tubes, the result would be fantastically large, hot, power-hungry, and unreliable. Buildings would be required to house what now fits inside a laptop. Cooling systems would dominate the design. Electrical consumption would be immense. Portable computing in its modern form would disappear. Smartphones, compact medical devices, digital cameras, satellites, navigation systems, modern vehicles, and data centers would all look radically different. The transistor did not merely make electronics more convenient. It changed the physical limits of what engineers could build. The story of the three Bell Labs scientists continued in very different directions. John Bardeen eventually left Bell Labs and joined the University of Illinois. His later work on superconductivity led to another historic achievement. Together with Leon Cooper and John Robert Schrieffer, he developed the BCS theory of superconductivity, and in 1972, Bardeen received a second Nobel Prize in Physics. He remains the only person to have received the Physics Nobel twice as an individual laureate. Walter Brattain continued at Bell Labs for many years and later taught, carrying with him the legacy of the hands-on experimental work that had produced the first point-contact transistor. William Shockley moved west and founded Shockley Semiconductor Laboratory in California. His company did not become the semiconductor giant he imagined, carrying with him the legacy of the hands-on experimental work that had produced the first point-contact transistor. William Shockley moved west and founded Shockley Semiconductor Laboratory in California. His company did not become the semiconductor giant he imagined, and his difficult management style drove away several talented employees. Those engineers, later known as the Traitorous Eight, founded Fairchild Semiconductor. From Fairchild came new companies, technologies, and leaders who helped shape Silicon Valley, including Robert Noyce and Gordon Moore, who later co-founded Intel. In a strange way, the tensions that fractured the original transistor team and Shockley's later company indirectly contributed to the creation of the very semiconductor industry that carried their invention into the modern age. The transistor's influence extended far beyond personal computers. Telecommunications became smaller and more efficient. Space exploration relied on compact, dependable electronics, while medical equipment, industrial systems, cameras, vehicles, and communication networks grew increasingly digital. Modern internet infrastructure and artificial intelligence now depend on semiconductor chips containing enormous numbers of transistors. Every search, video stream, bank transaction, or satellite calculation ultimately relies on solid-state electronics. The world is filled with machines that would have been physically impossible to construct with vacuum tubes at comparable scale. Yet the beginning of this transformation was remarkably humble. Return in imagination to Bell Labs in December 1947. There was no cleanroom producing silicon wafers filled with microscopic patterns. There was no automated factory printing billions of transistor structures. There was a small piece of germanium, a pair of gold contacts, wires, laboratory instruments, and scientists trying to understand why electrical current behaved strangely at a surface. The device did not look like the future. It looked like an experiment. Its creators were focused on a practical scientific problem, how to amplify and control electrical signals in a solid material. The larger consequences were invisible. That is often how technological revolutions begin. The first version is awkward, fragile, and limited. Its importance lies not in what it can do immediately, but in what principle it proves. Bardeen and Brattain's point-contact transistor demonstrated that a semiconductor device could amplify. Shockley's junction concept showed a path toward designs that could be manufactured more reliably. Silicon technology improved temperature performance and manufacturing potential. The integrated circuit allowed many components to be formed together. The MOSFET made dense, low-power transistor integration practical. The microprocessor gathered thousands of transistors into a programmable computing engine. Decades of scaling multiplied those thousands into billions, each generation built on the previous one. The modern personal computer is therefore not the product of one dramatic moment, but of a chain of discoveries, refinements, manufacturing breakthroughs, and engineering decisions. Still, the chain has a clear turning point, and that turning point occurred when scientists finally proved that a small solid device could replace the essential function of a vacuum tube. Today, when a processor executes an instruction, it does not think in the human sense. At the lowest level, it manipulates electrical states. Transistors open and close pathways. Logic gates combine signals. Registers store patterns of bits. Billions of these actions occur in coordinated sequences too fast for us to perceive. A single click on a computer can trigger millions or billions of transistor operations. A video frame, a spreadsheet calculation, a game character, a password check, or an artificial intelligence response all emerge from immense networks of microscopic switches. The remarkable thing is not that one transistor can do something complex. One transistor is simple. The power comes from manufacturing vast numbers of simple switches and arranging them into structures capable of extraordinary behavior. That architecture of complexity from simplicity is one of the defining ideas of modern computing. The transistor also changed the economics of technology. Vacuum tubes were assembled as individual components, while semiconductor manufacturing eventually allowed many devices to be created simultaneously across a wafer. As manufacturing improved, the cost of each transistor fell dramatically, even as performance increased. This economic effect made computing available to businesses, schools, families, and individuals. A machine that once required government or corporate budgets gradually became a consumer product. Then, computing moved into phones, cars, appliances, watches, and toys. Entire industries formed around semiconductor design and fabrication. Companies competed not only on how many transistors they could manufacture, but on how intelligently they could use them. Processor architecture, memory hierarchy, energy efficiency, parallel computing, and specialized accelerators all became major fields of engineering. The invention that began as a substitute for a telephone amplifier helped create one of the most important global industries in history. It is important, however, not to simplify the story into a myth of three men inventing the modern computer in one afternoon. Bardeen, Brattain, and Shockley stood on decades of earlier work in quantum mechanics, solid-state physics, radio engineering, materials science, and electrical theory. Researchers before them had observed semiconductor rectification and experimented with crystal detectors. Their breakthrough also depended on Bell Labs. Technicians, chemists, metallurgists, and engineers who purified materials, built equipment, and supported the research. Later generations transformed the transistor far beyond its original form. Atala and Kang's MOSFET was essential. Kilby and Noyce helped make integrated circuits practical. Semiconductor manufacturing pioneers developed planar processing, photolithography, ion implantation, and countless other techniques. Computer architects learned how to turn growing transistor budgets into useful systems. Software engineers created programs that gave those systems purpose. The history of the transistor is therefore a history of collaboration across generations. Still, December 1947 remains a powerful symbolic moment because it marks the point when the old electronic world and the new one visibly separated. Before that moment, high-speed electronic switching was largely associated with vacuum tubes. After it, engineers knew that solid-state devices could perform the same fundamental function. The consequences took years to unfold, but the direction had changed. Electronics could become smaller, it could become cooler, it could become more reliable, it could be mass-produced at microscopic scales. Once those possibilities existed, the path toward integrated circuits and personal computing became open. Imagine holding the original point-contact transistor beside a modern processor. One is a handmade assembly large enough to see clearly, built from germanium, gold, plastic, and wires. The other is a precisely manufactured silicon device containing billions of transistors, so small that individual structures cannot be seen without specialized instruments. The difference between them represents nearly 8 decades of accumulated engineering, yet both belong to the same story. One proved that a solid device could control electrical current. The other repeats that principle billions of times to create a machine capable of running operating systems, rendering three-dimensional worlds, editing films, designing aircraft, analyzing genomes, and communicating across the planet. That is why the transistor deserves to be remembered not simply as another component inside a computer, but as one of the foundational inventions of the modern age. Its greatest power came from its ability to disappear. As transistors became smaller, users stopped seeing them. They vanished inside integrated circuits, then inside processors, memory modules, sensors, and controllers. Their invisibility became a measure of their success. We no longer think about the billions of switching events taking place when we open a browser or save a document. We simply expect the computer to respond. Yet every one of those responses depends on a technological lineage that leads back to a laboratory bench in New Jersey. So the next time a computer starts instantly, a processor finishes a difficult task, or a tiny device performs work that once required an entire room of machinery, remember the unlikely beginning. John Bardeen was trying to understand invisible charges at the surface of a semiconductor. Walter Brattain was pressing delicate metal contacts against germanium and measuring the result. William Shockley was pursuing a vision of solid-state control and later developing a more manufacturable transistor concept. Their collaboration was imperfect, their personalities conflicted, and their invention evolved far beyond anything they directly built. But together with the generations of scientists and engineers who followed, they helped replace the glowing vacuum tube with the microscopic electronic switch. In doing so, they changed the scale of technology itself. The transistor allowed machines to shrink from rooms to desks, from desks to bags, from bags to pockets, and from pockets into almost every object around us. What began as a search for a better amplifier became the foundation of digital civilization. The modern PC, with all its speed, memory, graphics, and connectivity, is one of the clearest descendants of that breakthrough. Hidden deep inside its chips, billions of tiny switches continue performing the same essential act, controlling electricity with extraordinary precision. And from that simple action, the computer age was built.